Hey. Hi, everybody. So I'd like to do a guide video for the conservation of energy with the Pendulum Lab. Um, so just a brief summary. The goal of this lab is to investigate conservation of energy using a pendulum and its collision with another ball. So what conservation of energy is it's saying that energy is conserved before and after the collision. So this is the phenomenon that you're trying to investigate, whether or not this is true. And you're doing this using a pendulum and its collision with another ball. And you're looking at how far the second ball travels and using that to determine whether or not energy was conserved before and after the collision. Okay, so the theory, I start with the theory section. So I just like to say like what each question is asking and give you a little place to start from. So for number one, they're asking what is the potential energy of the pendulum at these different points in the experiment? And so what potential energy is, first thing you got to know is that potential energy is a form of energy that represents the energy stored in an object due to gravity. So for example, an object that is at a higher position, so an object that's farther off the ground will have more energy stored in it because it's higher off the ground. So we can write this in the following way. If I can do this, so you're going to get, so you're going to have potential energy. I'm drawing with the trackpad equals mgh. So here m is the mass, g is the acceleration due to gravity, and h is the height of your object. So this is, in this situation, this is going to be your formula for potential energy. So this is what you would use to answer these questions about the potential energy. And so for number two, though, they're asking you about the kinetic energy. So I'd like to say what kinetic energy is again. So kinetic energy is the energy of an object due to its motion. So it depends on how fast your object is moving as well as its mass. And these are the two things that determine how much kinetic energy you have. So in other words, KE, kinetic energy, equals half mv squared. So again, m is the mass of your object and v is your velocity or speed squared. So okay, so this is how you would do number two. So use what you know about the setup and the experiment, as well as these formulas to answer these top two questions. Okay, and I'd like to remind you that you can only have these specified variables in your answer. So for example, m, h, l, theta, big L, or g, as well as other like integers such as like 2 or a half. So you need to express your answer in terms of these. Okay, number three. So ideally, what is the horizontal velocity of the second ball immediately after collision? So this one, I think you can answer going off of the stuff up here, as well as what you know about the experiment. Just another note though is that when they say ideally, they're saying if we assume energy is conserved. So that's what ideally means in this situation. And I'll let you figure out number three. So number four, you can see, so how far does the second ball travel before it hits the ground? And this is actually something that the lab manual talks about, and you can They call it D, so big D in the lab manual. So look for that in chapter 10, and you should be able to figure out number 4. So again, these are all using things that are looked at in the lab manual. So no numbers or anything, just these variables. And again, please express your answer in terms of these variables up here. Okay, moving on to the procedure. So let's see. So number 1, what is the launch height in this experiment? So if you take a look at the data, which I can actually bring up. Where's that? So clear this. So looking at the data, you can see that the question has something to do with this number over here. So use that number for number 1. And for number 2, so what mechanism is used to hold the pendulum ball prior to release? So I encourage you to review the lab manual for this one, as well as the theory video on the website. And I'm not sure if they talk about it in the experiment video on the website, but either the lab manual or the theory video. So number 3, energy is lost from the system. What factors contribute to this energy loss? And this one, a good way to think about this one is to think about it in terms of assumptions that we made in order to derive our equation for how far the ball flies. So if you look at it on page 91 to 92 of the lab manual, it's a section called Concept Behind Experiment. They list certain assumptions that we make. And if you think about these assumptions, you can kind of, I guess, work your way back to what factors contribute to energy loss. Because in the lab manual derivation, all the theoretical calculations were assuming that energy is conserved. So if you see what assumptions were made to assume that energy is conserved, you can work your way back to what factors contribute to energy loss. Okay, data analysis. So let's see. So number 1 is, so this box up here. This box is referring to this first box in the spreadsheet. So that's what the data that you got to use. And for this D theory column, this is actually given in the lab manual how to calculate this. So you don't need to use any of the spreadsheet to do this last column. Just use the formula for D theory. So this is from the lab manual. But you need the data to do these first 2 columns. So, okay, so let's see. Next is number 2. So this double pendulum. So this is the data from the double pendulum experiment. And so if you forget what the double pendulum is, you can read the lab manual again. But this is using the data right here. So this double pendulum data corresponds to this box over here. And for this final column, you're going to be using equation 10.14. So if I bring that up, 10.14 is down here, 10.14. So this is the one that's related to the double pendulum. Okay, so next, we're going to look at this last box, so the bottom box. So this air resistance, this is the one where the pendulum just swings back and forth. And this is actually related to this air resistance data in the bottom here. So use that to fill this out, as well as as well as equation 10.13. So use this equation as well for this box over here. Or actually for this last column, use 10.13. Okay, so that's how you do that. And for the conclusion, I just like to remind you that for number one, agreement. So I can write out the formula for agreement. See if I can do this. Where's that? Okay. So agreement, we can call it S. So S equals, so your theoretical result. So like what number you got from the theoretical calculation minus what you got. So this is from your experiment, what your expected value is. So the number before the plus or minus is what you got. And then all this divided by the uncertainty of what you got. Oh. What you got. Okay, so uncertainty of what you got. Uncertainty of what you got. The theory minus what you got divided by the uncertainty of what you got, and all that absolute valued. So if it's negative, you can make it positive. Okay, so that's number one. And number two, for each trial, what is your confidence in the result? So confidence is actually the uncertainty divided by the expected value. So I think I'm saying this right, but I think expected value is this. Ooh. Expected value. So you have your answer is like expected value plus or minus your uncertainty. So this is what I mean by expected value is the thing before the plus or minus. Wow. So if you have like an answer like this, your confidence, so let's just call it C, your confidence is going to be equal to your uncertainty. Ooh. Divided by expected value. Expected value. Wow. Times 100%. Or whatever you get, move the decimal over to the right 2 spaces and put a percent sign at the end. This is how you do your confidence. Okay, based on number figure, okay, just look at figure 10.5 in the manual and you can see how to do number 3. Okay, so that's number 3 as well. So number 3, look at 10.15. And number 4, watch the experiment video on the course website. So then you can see what happens. It's not a very long video, it's a couple minutes, but they show the collision in slow motion. So look at number 4, or look at the experiment video on the course website. The link is on the La Lima page. Yeah. Okay, so virtual experiment. So I'd like to show you what this is. Where is it? So this is a virtual experiment. So it's what you would expect. Or it's actually pretty nice though. And you can see that this is just a model of the experiment. So this is the pendulum and this is the ball that flies away, and here's where it hits, where it lands. So what you can do is you can set the angle. So if you scroll down here, you can see you can change the angle of release. So how far up it goes. So if you see, if I change it to 80, it starts up there. But if I change it to 50, it only starts down here. You can change the angle of release, and you can do the experiment by clicking reset. And once you click reset, it'll say measuring. And when it hits the ground, it'll tell you how far it went. Okay, so for number one, you're gonna follow the instructions and average over your results, and just show the data in a data table. So show your 5 experimental results and then show the average of these results. So just like somehow write it in a table, I think. Okay, so number 2. So just do the same thing as number 1, but for different angles. And again, show your numbers and the averages. For number 3, so it says, assume that your mean represents a perfect impact in which there was no energy loss. So once again, they're saying, assuming that energy was conserved, then they're asking what is the initial height and the string length for each setup. So in the solutions, they actually do it only for 55, 65, and 75 degrees. So you only need to do it for these 3 degrees is that you have to find h and the string length. So what you can do for this one, since they're saying that you're assuming that energy is conserved, you can actually use your equation from the theory, since that's also assuming energy is conserved. And this is your equation for d. So the distance that the ball flies is given by d equals square root 4HL. So again, this is big L. So this is not what you're solving for. You want h first. So using your average. So for each of these 55, 65, 75, you're going to get an average value, and your average value is going to go in here. So you got a number equals the square root. Within the square root is this 4, h, and L. And they actually tell you that L is known to be 100 centimeters. So you can solve for h. And then after you solve for h, you're going to use h. You're going to use what you get for h, as well as your angle. You're going to use h and your angle to solve for little l, this string length. So you're going to do that first for the 55-degree angle, then you're going to do it for the 65, and then you're going to do it again for the 75. So you're going to get 3 values for h and 3 values for l. So each one corresponds to one of these angles. So just a hint, the equation to solve for little l is on page 93 of the lab manual. So you need to know the h and the angle to solve for little l, and to get the h, you use this equation, and d here is the average measurement that you got for each for like 55, 65, or 75 degrees. Okay, so that's the whole lab. Good luck, and let me know if you have any questions. Thanks.